Are you able to see my screen?
Yep.
And hear me?
Yes, we can see you.
Brilliant. Thank you very much. Thank you, Andy and Andrew, for organizing this wonderful conference. It is a joint conference, a joint talk between Ruben Pastilha and myself about sensing changes in illumination spectra over time. So from dawn to dusk, natural light changes from dim blue to bright yellow and smoothly black back to dim blue. This is the lighting under which we have evolved over millennia. So object colors are an interaction between light and surface. Without light, we would see neither color nor objects. Our visual system extracts stable object properties from the ever-changing light signal on the retina. We perceive objects to be stable in color despite these robust changes in illumination. In formulations of color constancy, we disentangle surface reflectance from illumination in the retinal irradiance signal. And the implication is that we discard the information about the illumination, having recovered the useful information about objects. Yet we do sense the illumination. And critically, we are able to distinguish between changes in illumination over time versus changes in object properties. So light not only enables us to see via the classical visual pathway, which we measure with spectrophotometry, visual behavior, and conscious reports of perception, but it also enables us to tune our physiological rhythms to the environment. So light elicits non-visual effects as well via a distinct neural pathway, which originates in the IPRGCs and which contain melanopsin. Melanopsin signals mediate pupil size, circadian photoentrainment, melatonin suppression, and modulate alertness and other physiological functions through monitoring the overall irradiance of light. But the projections from the IPRGCs are far-reaching and overlapping, and the accepted objective indicators of visual pathway activation, including, as I said, spectrophotometry, et cetera, in fact, might be influenced by non-visual activation. So both the visual and the non-visual systems evolved under natural daylight and are therefore likely tuned to its properties. Natural daylight is a mixture of skylight and sunlight modulated by interaction with the atmosphere and varying with the time of day, geographical location, and other factors. So daylight is broadband, as we see here, with energies at all wavelengths, and its spectra take on characteristic shapes, with the chromaticities falling on the daylight locus. Now, the closeness of the S-cone axis to the daylight locus, seen here, suggests that the evolutionarily older S-cone mechanisms dating back to our dichromatic ancestry function to detect changes in irradiance, light being light detectors, not differences between object reflectances. So our color vision system evolved from light detection to object detection, we might say. Just as an aside, Turner captured these chromatic properties of daylight perfectly in his color beginning watercolors. The distribution of chromaticities in this watercolor fall almost perfectly along the daylight locus. But the key to the properties of daylight are its temporal dynamics. It changes over the course of the day due to changes in solar elevation, atmospheric conditions, clouds, fog, etc. And it's dynamic, and our body's physiology is synchronized to the natural changes in light over this light-dark cycle. And these temporal variations in spectra, in turn, can convey important information about environmental conditions, such as time of day, weather, wind, obstructive objects. So here we ask, do we respond to these dynamic properties of daylight? Does the human visual system perceive these changes in daylight spectra? And does the non-visual system follow these temporal changes in daylight and respond to these with behavioral variations? And today, what we want to do is discuss two studies, a laboratory psychophysics study and a real-world study of behavior under changing illumination conditions. But first, let's take a closer look at the temporal dynamics of daylight. Light changes in chromaticity and overall irradiance through the day. As we see here, we see measurements of spectral irradiance of downwelling light from one day in October 2018 in northeast England. The irradiance rises at around 7 a.m. and falls around to 7 p.m. The chromaticity changes most rapidly at dawn and at dusk, almost symmetrically, becoming bluer at the start of dawn and then reversing direction to become yellower as the radiance increases. And at dusk, the changes are the reverse. We've looked at illumination changes in databases from different geographical locations, and we see here very similar changes on the west coast of USA in the DiCarlo and Mondel database. In both, the largest changes in CCT, chromaticity, are at dawn and dusk. And the massive rapid changes in irradiance during the day are due to clouds or the movement of sun behind obstructing objects. But at dawn, we have decreasing blueness and increasing brightness, and at dusk, increasing blueness and decreasing brightness. So in ongoing analyses, we're examining a variety of daylight spectral changes in different geographical locations and conditions. And always the most significant changes in chromaticity and lux are at dawn and dusk. And here we see a plot of the velocity of the chromaticity changes with the arrows representing the velocity of the change. We've analyzed the chromaticity and lux changes in the database from Granada, from Hernandez Andres. And we see that where there are clear skies in Granada and less influence from clouds, we have smooth changes in color temperature and in lux, which follow different patterns for different months of the year. So both the non-visual and visual systems are likely to be sensitive to these directional changes in chromaticity and lux throughout the day. For example, we know that neurons in the suprachiasmatic nucleus of mice that receive input from the melanopsin-containing IPRGCs do respond to temporal changes in the chromaticity of daylight. But how people sense these temporal changes in illumination is complex and not yet understood because of the interaction between visual and non-visual responses and the interaction between circadian phase and physiological response to changes in spectral content. We do know that there are significant overlaps in spectral sensitivity of the receptors, and there are also overlaps in the output locations of the projections from these pathways. Research, of course, into the effects of and the interactions between the non-visual and visual pathways are ongoing, and as Manuel Spitzkin showed in his lovely review, the number of papers on this topic is increasing rapidly. We can characterize the effects of light on the non-visual pathway via its melanopic lux, the content of melanopic power in the light. And we note that the melanopic changes during the day tend to follow the photopic changes of light. We also know that melanopic content affects melatonin release regardless of photopic lux. We've shown that both white light and blue light of differing photopic power but equal melanopic power have the same effect on suppressing melatonin when that light is delivered at night. But we also know that the timing of the melanopic stimulus is crucial in determining the effects on behavior. So the question is, does the temporal variation in illumination per se affect non-visual behavior during the day? This is the question we asked in a real-world behavioral study. In collaboration with Arup, an engineering and design company in London, and with Leitmotif, who make spectrally tunable multi-channel LED lamps, we carried out a 9-week study in the offices at Arup to compare human behavioral responses to different lighting conditions. The study was led by Alish Linas, who was a finalist in the SLL Young Lighter 2020 competition recently. We compared responses of individuals to pre-programmed dynamic sequences of light with static light conditions. And we also had a condition in which we matched daylight in the outdoors, the building, in real time, which I'll talk about in just a moment. So just to briefly go through the conditions we used, we compared static conditions, the baseline condition of the fluorescent lights, which were already installed in the office for 2 weeks, with dynamic conditions, 2 different sequences. Sequence A, in which the photopic melanopic lux and the correlated color temperature, that is the apparent chromaticity, the visual chromaticity of the lights, change in concert with each other, with the light changing from brighter blue in the morning to dimmer yellow in the afternoon. In sequence B, both the brightness, the photopic lux, and the chromaticity of the light were held stable, and only the melanopic lux changed from higher levels in the morning to lower levels in the afternoon. These were compared with another baseline condition delivered by the lights to mimic the fluorescent lights, and with a daylight matching condition. Observers were subjected to a rather large battery of behavioral tests, completing questionnaires and performing a visual attention task in the morning and evening, and also wearing actigraphs with which we recorded information about their physiology. I won't go into those in detail here. But I want to describe just briefly the method for recording and playing back the daylight in real time to mimic the outdoor daylight conditions in real time with the indoor lamps. So a spectrometer was installed in the roof of the building and connected to the internet and recorded its recordings of real-time daylight changes on a cloud server, and then replayed them to the spectrally tunable lamps, which were installed in the ceiling, whose 7 channels with different weights enable us to match any desired spectrum. So the recorded light outside was replayed indoors, and the matches between the outside illumination here shown in a dashed black line matched pretty well the inside spectrum delivered via the lamps, as you can see here, for 3 different times taken from the 9th of April 2019. So the measurements pretty well validated the performance of the system. The indoor color temperature of the lamp's output matched pretty well the outdoor color temperature of the light, ranging here, as you see, from a little above 6,000 Kelvin to a little below 5,500. The photopic lux, though, was clamped between 300 and 500 lux at desk level, so didn't match completely the large variations in irradiance outside, because this was a real-world experiment in which people were continuing to work during the experiment, and we had to conform to well-building standards. The most significant result from this study, the most striking difference between lighting conditions, were in the subjective responses in the free text comments. People did not like the fluorescent baseline or sequence B, in which only the melanopic lux changed, not the photopic lux or the color of the light. People were sleepy, bored, confined, de-energized, felt like they were working at night. In contrast, under the naturally dynamic lighting conditions, people said they felt more lively, more alert and focused, and felt more comfortable in general. And these free text comments were borne out by quantitative results of the questionnaires that individuals performed. We asked people both, as I said, for free text comments, and independent raters rating these comments from a valence of +3 to -3 found that, again, the naturally dynamic light sequences, sequence A and simulated daylight, were most preferred, as well as most liked, as well as seemed to be most pleasant. And these subjective effects were significantly different between lighting conditions, but not dependent on the time of day. Are these preferences due to visual or non-visual effects? That's a critical question. So it's important to note that the effects on the objective visual attention task largely did not differ significantly between lighting conditions. There was a significant improvement in the D prime with sequence A, but there were significant differences between morning and afternoon in all the measures for all the lighting conditions, and I don't have time to go through that. But one thing that's critical to note is that when asked, how well can you see, people significantly disliked and felt they didn't see well under sequence B, which was the melanopic lux changing only condition. And it's important to note that this condition, because it modulates different regions of the spectrum differently, has a rather bad effect on the color rendering index of the light. So there might have been some subtle color changes which people did not like, but generally they felt that visual clarity was poorest in this lighting condition. And also, although both sequence A and sequence B, the melanopic change only condition changed dynamically, the sequence E, the naturally changing dynamic sequence, is clearly rated higher in all the attributes of atmosphere, which suggests that the visual effects of the change in color temperature, the fact that it becomes yellower and dimmer in the afternoon, are important in influencing the overall non-visual subjective response. And it's also important to note that although both the sequence A, in which all the characteristics change in concert, and daylight matching are most preferred, these actually differ in terms of their dynamic shape, in terms of their dynamic profile, so that in the daylight matching experiment, it's not the case that the light every day gets dimmer in the afternoon. So perhaps people just prefer variety, changing light regardless of the actual way in which it is changed. But we come to the question of whether people are actually able to perceive changes in daylight spectra. And this brings me to the laboratory psychophysics task, which Ruben will now describe.
So thank you, Anya. I guess you can hear me?
Yep.
Okay, thank you very much. So yeah, so earlier studies have looked at temporal illumination changes, a few with display simulated stimulus changing in a linear profile, and more recently, a few with the periodic temporal profile. However, none of these studies were specifically concerned with speed limits on the detectability of natural illumination changes over time. And to do that ourselves, we decided to go with Lightroom illuminations with changes in a linear profile. So we set up a Lightroom equipped with a spectrally tunable light system with 10 LED channels that allows to fine-tune the illumination spectra. And we use that to obtain daylight metamers. And the Lightroom itself had matte white walls, allowing for the participant to be, next slide, please, to be fully immersed in the chromaticity of the illumination because of the white matte walls. So while looking at the viewing scene, with a semi-free gaze between those 5 crosses of the scene, and the scene itself was purposely confined at the most uniform region of the wall in terms of brightness. So observers with normal color vision were selected, and they sat down in the Lightroom at medium viewing distance, and they were wearing a black cloth over their clothes to control against potential mutual reflections from their clothes onto the white walls, and therefore helping to maintain the congruence with the calibration condition. We also included noise cancelling headphones to avoid influence from any potential auditory cues from the lamps. And in addition, the participants were using a gamepad to input their responses during the psychophysical testing. So the conditions tested corresponded to Lightroom simulations of daylight transitions. And we used 4 base lights. The base lights corresponded to the starting color of the possible illumination transition and were selected along the daylight locus, 2 at the extremes of the daylight locus and 2 near equal energy white. Their spectra are on the left chart, identified by their correlated color temperature in Kelvin. And on the right, we have their chromaticities. And for each base light, we tested two directions of transition, which corresponded to the daylight locus direction. So warm changes and cool changes for each base light. So in total, we get 8 types of illumination transitions. And we tested those at different velocity levels. So to measure detection thresholds of illumination changes, we used a method of constants on one interval forced choice yes/no task. And here we have the trial structure represented over time. The trial starts with 2 seconds of noise stimulus to mask the chromatic state between trials. And the noise chromaticities were randomly generated, but averaged down to the chromaticity of the base light that was being tested. After that period, we have 5 seconds of top-up adaptation to the base color, which is then followed by the counterized sound start, signaling the beginning of the main stimulus, which is a perceptually smooth illumination change. In this case, the illumination is becoming bluish. And the change is done between the base and end colors, and that amount of change, which is the delta E expressed in CIE-LUV, is varied across trials, while the duration was held fixed at 10 seconds. And that's how we varied the velocity of changes between trials. When the change finishes, there's a sound N, and the participant is forced to choose between one of two choices. Yes, I saw a change, or no, I didn't see a change, between the sound start and end. All of the stimuli in the trial have fixed illuminance at photopical level, and the color of illumination is expressed in CIE-LUV, assuming the base color as the white point. In this trial example, the illumination was changed to cool colors of the light locus, but we had 2 other types of trials. So in this case, warm change trial, and we also had change absent trials for control. So during the psychophysical procedure, each block of trials would start with 2 minutes of adaptation to the base light, followed by a random sequence of 84 trials, half target absent trials with no change, and the other half target present trials with cool change and warm change. After that, the participant would take a break before starting a new block of trials, and for each light, we did 3 blocks of trials, resulting in the total of 252 trials per light. So from the method of constants, the data that we collected, we can calculate the thresholds for each participant, and we have the average result across participants represented for each base light and type of change, cool change or warm change. So repeated measures and over showed the significant main effect of CCT of base light. And post-hoc corrected comparisons of means also showed significant differences between directions for all base lights except D65, which is the second light from the left. And in addition, there was a significant interaction between CCT and direction of change, which was a crossover interaction. So as you can see, that for warm changes, the thresholds become lower for warmer base lights on the right, and the opposite happens for cool changes. So thresholds of cool changes increase for warmer base lights. So overall, there is no main effect of direction because the differences in thresholds are opposite for CCTs at opposite ends of the daylight locus. So if we go to the next slide, on the right panel, we have the mean thresholds for changes away and towards the nominal neutral color, but only for the 2 most extreme base lights. They were the ones that had the most significant difference between the 2 directions. And as you can see, there's larger thresholds for towards neutral. So thresholds for towards are 3 times further away. If we go to the next slide. Okay, so thresholds for towards are 3 times further away from the grand mean than the thresholds far away. So therefore, thresholds towards neutral seem to be the main driver for the direction-related differences that we get. So now that we start have a notion of the detection thresholds, you can compare it to measures of actual daylights from the databases that Anya was talking about. So on the right panel, there's on the left panel, we have an example of a day for the DiCarlo and Wendell dataset. We analyzed, we did an analysis for each month and estimated by doing polynomial fits to the daily data. We estimated the velocity of, or the maximum velocity of change, assuming all possible white points, and those white points corresponding to the all possible daylight colors. So on the right chart, we can see that the value of the maximum velocity of daylight is way below the range of detection thresholds we found for the daylights we tested in our psychophysical experiment. So the fastest daylight change was 22 times slower than the minimum illumination velocity discriminated by the observers in our experiments. So for, at least for this particular data set, it's clear that the maximum velocity of chromaticity change is much slower than the minimum speeds perceived and will be undetectable based on the thresholds that we get. However, the analysis is still ongoing, and although the study results are solid, they apply to isoluminant changes only, at least for now. So in conclusion, just a quick summary of this study. The crossover effect suggests that sensitivity to the light changes depends on CCT of base light and chromatic direction in a crossover interaction, where cool changes become less noticeable for progressively warmer base lights and vice versa. And in addition, the data can be interpreted as there being a neutral bias, in the sense that changes towards neutral are less easily discriminated than changes away from neutral. And we also observed that for this specific example of daylight data set, the daylight changes are too slow to be detected. Okay.
So we can conclude also from the behavioral studies that people prefer subjectively dynamic changes in illumination. And in some cases, these dynamic changes also elicit better performance. People also seem to prefer warmer and dimmer lights in the afternoon for visual clarity. And yet people also prefer dynamic changes regardless of the direction. So we might conclude that people are able to respond behaviorally and non-visually to dynamic changes in illumination, which they are unable to perceive visually when we pull both studies together. Thank you very much.